So I'm told it's the green button here. Hello, everybody. It's really nice to see you. I've gotten a chance to talk to several of you this afternoon, and it's really exciting time in computing and in the analytics field. So before I get into the whole topic of analytics and cognitive, I just want to start with some sort of stage setting. So when I look at technology and emerging technologies, I think that three key principles. First of all, revolutionary technologies that really change everything, take a lot of time to evolve. They don't just appear and then they're overnight successes. And dramatic changes like we're seeing with cognitive and advanced analytics happen when technology is mature enough and when it's ubiquitous enough and when the foundations are in place. That's when they happen. And then when these forces come together, that is where we see technologies that absolutely can revolutionize industries and governments and really the planet. So the bottom line is that all of these factors have to converge before these revolutions occur. So I know there's a lot of talk right now about the idea of digital disruption. Well, what does that mean? What that means is that, again, those technology factors and timing and ubiquitousness all come together and suddenly change occurs. But again, it's not overnight. So right now, we're looking at a lot of technologies. I mean, the common example is Uber. Why does Uber happen? Uber happens because of the technology changes, because really what makes Uber possible is the internet and advanced analytics. Without that, they wouldn't exist. And that goes for a lot of other changes that we're seeing really in many industries and many government agencies. So now let's get to the topic of hand around cognitive. So what cognitive computing is, and I think there's some misunderstanding about it because this is really a composite area. It isn't just sort of one small thing. It really is the ability of humans to work in collaboration with machines and advanced analytics to correlate huge amounts of structured and unstructured data to come up with results. So it's a problem-solving technique, and it involves hardware and software. And the idea in the long term is that we have this collaboration that begins to approximate or leverage the natural cognitive processes that we take for granted every day. But let's put this in some context here. What is the problem with the way we traditionally create software to run our organizations? Well, we start with logic. And we start with logic based on how do we do things now? What are the processes? What's important? Which is fine if you can go, change things every couple of months. But as we all know, especially in large, complex organizations, sometimes that software that you assumed would last for a year or two ends up lasting for 20, 30, 40 years. So programs are really not designed for business change. Data is ingested after the fact, and programs are based on outcomes and assumptions about outcomes. So a traditional system and a traditional way of creating systems really is something that we have done for the last 50 or 60 years, and it really can't anticipate the future. So there are huge flaws in that model. So how is cognitive different? I would say that cognitive is based on the idea that you begin with the data. You don't begin with current logic. You let the data lead you to what the outcomes are. And this is a very different way of thinking of software and the role of software in our organizations. So if you begin with data, that means you begin by looking at patterns. You look at anomalies. You take data and you see what you can learn from it. Just the example in a smarter city, for example. What can I learn about traffic patterns? What's a normal traffic pattern for 3 o'clock on a Friday afternoon? If suddenly no traffic is moving at all on a Friday afternoon, that's an anomaly. So I'm going to learn something from that pattern of data that I wouldn't necessarily learn from creating a program for that. So we also assume with a cognitive approach, because it's data-oriented, that there isn't one right answer. The answer is probabilistic. It depends on what's going on. So you start with a hypothesis based on what you expect things to happen, what could happen, and then you test that. Now, cognitive computing, rather than being based on process logic, is really based on how humans learn, how they observe the world, and how they leverage data to make correlations between what's happening around them. I'll give you a great example that I love using. If you're walking down the street, you could be a 10-year-old child or an 80-year-old man, and it's a beautiful summer day, and you see a tree with all the leaves falling off. Now, is that normal? Well, if it's the summer, and if the leaves are falling off, based on your experience of what happens in summer with leaves, the type of tree it is perhaps, you will come to the conclusion that there's something wrong with that tree. So that's based on, it's not something that you stand there for an hour analyzing the situation. You're using a correlation of what you know, how the world works, what you know about trees and weather. And that's complex logic, but it's all based on data. And that's also how our brain works. Think about what it takes for a machine to replicate the child learning to ride a bike. Think about all the things that the child learns from experience that go into that, and you realize how complex a process this is. So we as humans learn from everything from reasoning, deduction. We deduce that the leaves falling off the tree means that it's a diseased tree. If the same thing happens in February, well, we don't think that the tree is diseased. Those leaves should be off in February. Now, all of this is very important in cognitive computing because, in fact, all of these senses are seen, which is one sense that you can actually apply to cognitive computing. Hearing is just zeros and ones, just put in a different form. Even smell, can I detect an area where there's a gas leakage? Now, perhaps I can make that part of a cognitive process. Taste, touch, same idea. So if we think about a lot of this may be structured data, so we may have something like music that has very specific structures. Every type of data has structure. It just depends on what it takes to get that structure and understand that structure. So for example, text, unstructured data, there is structure in it, but you need time and effort to figure out what that structure is and applying technology. So I know this morning we had discussion about what big data is. And clearly what we're talking about is lots and lots of data. And I've always made the point that actually big data is really small data. Because you actually, if you had, 15 petabytes of data, that really doesn't give you an answer. It's getting to those patterns and to the answers that is really important here. Veracity is something that we don't always talk about when we're talking about big data, but in some ways it's one of the most important aspects. And veracity is the truth of that data. So I can have a huge volume of data and I can go do all of my analysis, but my data is not clean. My data is not verified. I put data set A, B, C, D, and F together, and it doesn't really make any sense, but I can come up with an answer. So how clean my data is, how truthful my data is a really important point to this. Earlier, there was a session talking about Spark, and that's where the idea of speed comes in. There are times when speed is not the most important issue. So if I'm doing analysis to figure out the cause of a disease, I may expect to spend 6 months analyzing that data. On the other hand, if I'm looking at a sensor on a train to know whether there is a problem or a defect, I really have to be able to find an answer in real time to tell the train to stop if there's a fire on board. So big data is very important because it is a part and an essence of cognitive computing. One of the things, so the traditional way, if we set up a data warehouse, we do a query, that's based on the fact that we sort of know the answers we're trying to get to. We sort of understand that what we're trying to do is figuring out what are sales going to be in region 4, and based on the history over the last 5 years, what could I expect now from the following month? So I sort of know what questions I'm going to ask. I've already pre-established the context. It's all my regions for selling coats in the Northeast. So all that context is sort of pre-understood, and I'm not really worried about that. I know what I'm looking for. One of the things we start doing with cognitive computing, it's basically being able to get to the point where we're able to let the data lead us to what we're looking for, because we may not know the answer. If for example, in a healthcare scenario, I have a patient, and I'm not quite sure what's wrong with that patient. And I happen to have read a journal article 2 weeks ago, and it mentioned something. Gee, I just read that article. That sort of sounds like what's wrong with this patient. So let me look and see if that's the problem. But, there may be 200,000 journal articles published a year. That doctor happened to be really lucky that they read that article at the right time, at the right place. The fact is, we have so much knowledge and so much data created by humans that is really incredibly important, but we can't always put them to good use. So that's that's where I'm talking about starting with the data. So if we can begin to automate that data, put that data in context, use machine learning algorithms to help us start understanding what it means. Where are patterns? What can I find out when I don't even know what question to ask? And that is really one of the powers that we're seeing around cognitive computing. What can I learn when I don't know what the question is? In another situation, it may be something like, use a retail example. Or a travel example is a great one. I want to go on vacation somewhere warm. So what question do you ask? Well, if you're going to a traditional site, you would say, well, I want to go on vacation. Where do you want to go? Well, I don't really know. I just want to go somewhere. Which week do you want to go? Well, I'm not really sure. So again, it's assuming that you already know what you want to find out. So if I put in, I want to go to Bermuda, I want to go February 10th, and I want to go to this type of resort, you're okay. If you say, I have 3 kids, I want to go somewhere warm, I don't want to go there, but I want to go somewhere that has this type, and it has to have this type of children's program, but it also you can't do that. So a cognitive system, if it starts to learn about you, can really, again, you don't know what question to ask. If you knew exactly what the answer was, you wouldn't need a lot of help. So the idea of having a type of system that combines big data, which means lots of data to help you come up with those patterns and anomaly, machine learning algorithms, and a cognitive approach that puts data in context. So machine learning, it's a discipline of computer science. It's based on statistics and psychology. It includes many different types of learning algorithms, really focused on looking at patterns from data rather than an explicit answer to a question. So what we're already seeing is that this type of data-driven application can be applied across a lot of different types of organizations and a type of problems being solved. So what would it mean in governments? Governments are always looking for better ways to support citizens. So how can I create a way for citizens to be able to access the right social service at the right time based on my needs? So if I am somebody who is 76 years old and I'm looking at these social services, it should lead me in a different direction than if I'm somebody who is 32 and I'm looking for support. So being able to really set up these citizen services, because expectations among up-and-coming citizens is that they can go to a website and get immediate answers to complex problems. You know, clearly we are seeing a lot of applications of this cognitive approach to intelligence agencies, to not just say, oh, here's a cyber attack, let me stop it, but here are the 3 or 4 clues that are patterns that indicate that in 10 minutes somebody is going to do something bad because based on this pattern. Registry of motor vehicles, probably the bane of most people's existence, can be streamlined by putting a lot more intelligence and a lot more data into these systems. So to do a cognitive system, again, requires leading with data, providing clues when you don't know what questions to ask, leading with a lot of interaction and a lot of context. And what we're beginning to see happen, because if we were talking about this even a year and a half ago, you'd have to be the smartest data scientist on the planet to be able to do this. What we're starting to see is that these platforms are being abstracted so that in fact there are tools, there are APIs, and development tools that are making it easier to begin to build these. So just to give you a little bit of a sense of what we're talking about, the type of algorithms and type of approaches, and I won't go in this to detail, I don't think we've got that much time, but these are 3 of the key approaches. One is supervised. This is where you sort of, the system is going to be programmed based on these algorithms to detect or match patterns. And what you do is you continuously train the system to say, am I getting the right patterns? Is it working? So you're working with the system to determine that. And you sort of have a direction. You sort of know which way you're going. Reinforcement learning is something where you have a system, now you're looking for feedback. Is this working? If I ask it this question and using a natural language processing engine, is it right? So that's where you continuously, ask a question, is it giving me the right response? No, you're wrong, let me feed you more data to improve the performance. And then unsupervised, you really don't know where you're going here. You are doing gene screening. You're trying to discover a drug. You really can't tell it where you want it to go. So what you're saying is, I'm going to feed you huge amounts of data, and you go discover the patterns that I could not see in a million years. My brain doesn't work that fast, and even if I put 10 of the smartest brains on the planet together, they will never discover that. So again, deep learning is sort of more along this spectrum, where we are looking to solve really complex problems by sophisticated layers of abstraction to be able to do a lot of parallel processing, parallel learning, a lot of models, and there's actually a lot of work at some of the major research institutions. Can we sort of simulate the function of the brain? So these are really, early type of processes. There's, if you are interested, there's a project called Baby X. I don't know if any of you have seen this. It simulates a baby and the way a baby reacts to stimuli. And it's all a computerized system, and the scientists use an image of their child to create this, and it sort of gives you sort of an inkling of what could be possible someday. And this deep learning is already starting to be applied in areas like security, where there's so many different ways that we can be thwarted, and then drug discovery that is so complex. Now, I won't spend a lot of time on this because there's we could spend hours on this, but I just wanted to give you a sense of what the elements are here. So at the very bottom, what we're looking at, sort of, this is the foundational infrastructure. This is anything that you would see with any ordinary system, a cloud, storage, processing. So there has to be these deployment models underneath it all. Then you have all of your data sources and metadata and ways to access those sources, both internally and externally. And then, how do you make sense out of those, whether you're doing extraction of features, whether you're doing some sort of deep learning, and then using some natural language processing. One of the key elements to creating a cognitive system is the idea of a corpus. And you could almost think of this as a huge database, often with unstructured data from related sources. So if you are in a city situation, you would be collecting data about traffic patterns and about people and about the city and characteristics of the city, and background research about studies about how people live and weather patterns, things like that. So all of that would go into ontologies and corpuses. And then, of course, there are many analytical services that you'd apply to all these data. Then if you notice on the top there, it says model, generate a hypothesis, score the hypothesis. So once you have all this data and it's been curated, now you say, okay, based on all this data, I have a hypothesis. I think that between 3 and 5 in the afternoon, traffic is horrendous. So if I change the traffic pattern like this, I think that I would get rid of traffic jams. Maybe that's my hypothesis. So I model that, and then I apply my data, and I see, does this work? And then I test it, and I don't have enough data here. I add data. So what I'm starting to do is I'm starting to put really a knowledge base together that looks at, it really sort of creates a world, which we tried to do with artificial intelligence 30, 40 years ago. The problem was, in those days, you had to hand input all of the data you wanted. You had to come up with, you had to pre-think and you had to pre-know everything you wanted to do. With a lot of the advances in big data and analytics, now you can take this data, you can bring it together, you can create new ways of collecting and managing data that really starts to transform what we're doing with data and how we can use data to just do things that were never even imaginable. So again, so what I'd like to emphasize is what we're really talking about is a life cycle of knowledge management. You know, what's my hypothesis here? What am I trying to solve? What are the right sources to help me solve that problem? Then bringing them together. And I say, well, is this right? And well, no, I'm missing data. I have nothing here about weather data. And then training the system. So it becomes really a life cycle. And by the time you're done with this, and you know, it could take, you know, years, depending on the complexity of the area, to start feeding more and more data in until you really begin to learn. A lot of this will also be based on knowledge of individuals, people who really understand what their world is and are experts. So it's capturing the information about what people know and what they learn. A lot of learning, you know, you talk to somebody who's been in a field for 30 years. They, let's say a physician walks into the room of a very sick patient. They spend 5 minutes and they say, I know what it is, it's XYZ disease. The physician that's been treating the patient, who's had 10 years of experience, had no clue. How did this doctor, who only spent 5 minutes with the patient, know? It has to do with experience and their life cycle of knowledge. So how do you combine that? How do you capture that rich experience and that rich knowledge? And that's really where we're going with cognitive computing, and why it's really hard to just say it's not a database. It's much more than that. It really is a combination of a lot of ways of dealing with the world. So I started off by talking about the fact that when we look at technology and the way technology exists, that these transitions are happening before our eyes. But they take time. Sometimes they take 4 or 5 decades before something that seems relatively obvious becomes practical. So as we move to cognitive computing and big data analytics, it's really important that over time we shift away from programming models. Will this happen tomorrow afternoon? Absolutely not. We have 20, 30, 40 years of entrenched programs. We have ways that people are used to working, and people find change very difficult. So this doesn't happen overnight. But the shift is beginning to happen. It's beginning to happen in cities, in governments, in healthcare, in transportation, in travel, all sorts of different industries. And it won't happen all at once. It'll happen in elements where there's enough data, where there's enough knowledge, and where the areas are new enough that people are willing to take those type of risks. So this emerging technology that we're seeing, cognitive, can really be a secret sauce for innovation, much faster and much deeper than what we're used to in the world. And if we do it right, and if we experiment, I think a lot of this has to do with being open to experimentation. You can't sort of solve all problems all at once. You can't create big science projects, everything you want to do, because it's not practical. But if you select a specific domain, a small problem, and apply this type of data-driven analytical approaches, you can transform something very important. And there's nothing like success in being able to prove that there's a better way that really helps everybody, that's going to move things from impossible, creating systems based on old assumptions and old processes. If we think back to the assumptions we made about technology 20 years ago, and if you think about what's happened now, how many of us would have predicted the world we're in today with technology? I don't think any of us would. If you think back, it was only probably 50 years ago that our cell phones have as much computing power as a mainframe computer that would take up a city block. So transformations do happen. And this is one that I know it's hard to visualize, that there will be a time when you don't build a system based on your assumptions about logic today. You'll start with data, but I do predict that that's going to be the next time we have a meeting like this 10 years from now. It's like, well, obviously you don't start with assumptions about yesterday. How stupid can you be? Not really. No, we're all smart. But in fact, that's where we are seeing this transition, and it will not be obvious, I would say, probably for another decade. But it is the future, and I think by investing in this and thinking this way, it has tremendous ability to transform the world, and I think it's very exciting. I think I have a few minutes for questions. Do I?